Bernoulli's equation, which you see written here, relates the velocity of a fluid to the altitude of the fluid to the pressure in a situation like the one that we've seen with the water flowing out of a bottle. And we analyze this using potential and kinetic energy conservation, remembering that the potential energy lost by the water that vacates this part of the bottle will be manifested as the kinetic energy of the water exiting the bottle. Obviously we have a relationship between the altitude of the water and its velocity. That is, we have an altitude change from here to here, and we have a velocity difference. We have velocity essentially zero, a very small velocity here, and a great velocity here. If we had a greater difference in altitude, or the depth of the water, we would have a greater velocity down here. So obviously altitude and velocity maybe have something to do with one another. Clearly also the altitude at which we look at the water has something to do with the pressure at that level. If the altitude is here, the pressure is less than if the altitude is here. Bernoulli's equation tells us that this is a specific relationship among the three quantities: velocity, altitude, and pressure. I'll mention also the density rho, and that's to be distinguished from pressure, capital P. The density rho for air and other compressible fluids can also change, and that adds a fourth variable. But right now we're dealing with water and liquids, actually, where the compressibility is very minimal, and as a result rho remains pretty much constant. Now, if we compare 2 points in this liquid, a point at the surface and the point where the water exits the container, let's make the convention that altitude h is 0 at the altitude of the hole. Okay, so we're going to call the point up here where the water surface meets the air point 1. We're going to call the point where the water exits the container point 2. h1, the altitude at this surface, is going to be measured relative to the altitude of the hole. And of course h2, being the position of the hole, is going to be 0 if that's our reference point for measuring altitude. So altitude is measured from the hole. Here the altitude is 0, and we say h2 is 0. State 2, h2. Here the altitude is, let's say, 17 centimeters. That's a fairly typical altitude that we measured for the water surface at the beginning of the experiment. So h1 is 17 centimeters, meaning this point is 17 centimeters higher than the reference point, which is here. Now the pressure. What's the pressure at this point, and what's the pressure at this point? Well, the pressure at the surface here, where the water meets the air, is pretty clearly atmospheric pressure. 1 atmosphere, approximately 10 to the 5th pascals. How fast is the water at the surface moving? Not very, compared to the velocity that we have down here. Since the velocity that we have down here is so much greater than what we have up here, we're going to say that this velocity is approximately 0. And remembering that velocity occurs as a squared term in Bernoulli's equation, we're even more justified in saying that this velocity is approximately 0, because when you square two velocities, if one is a lot less than the other, the square is going to be a whole lot less than the other. And that's going to be the case here. What's the state at the hole? Obviously h2 is 0, because the hole is our reference point. P2. Okay, we're talking about water at the instant it exits the container. Well, at that instant, it's out in the air again, and its pressure is 1 atmosphere, or 10 to the 5th Pascal. And V2 is the unknown quantity that we want to predict using Bernoulli's equation. Now, you might be a little confused about why the pressure is 1 atmosphere here. I said kind of glibly that, well, the water we're at the instant the water exits the hole. Isn't the pressure right on the other side of that hole much greater than atmospheric pressure due to the depth of the fluid? Well, not quite. This is because right on the other side of the hole, the water is moving. We kind of have streamlines in the water. The water kind of streams down toward this hole like this, increasing its velocity as it approaches the hole. As the velocity of the water increases, the altitude, there's not much altitude difference in this region. The altitude stays pretty much the same. The pressure, therefore, has to decrease in order to keep this quantity constant. Okay, an increase in velocity with constant altitude means pressure has to decrease or the sum would not be constant. So pressure is gradually decreasing within the container as we approach the hole. As the water moves faster and faster, we have a decrease of pressure. And at the instant we exit the hole, the pressure actually has gone all the way down to atmospheric pressure. And we can then determine velocity V2. Now Bernoulli's equation tells us for this situation that the 1/2 rho V squared plus rho GH plus P quantity at state 1 at the surface is equal to the 1/2 rho V squared plus rho GH plus P term or sum at the hole. So this sum equals this sum, where the 1s here indicate that these are the velocity, altitude, and pressure measured at this point, and the 2s indicate the velocity, altitude, and pressure measured at this point. With the given information, we can rewrite Bernoulli's equation, same equation we just wrote. We note that pressure 1 and pressure 2 are both atmospheric. Since they're both atmospheric, we can subtract atmospheric pressure from both sides, and these pressures are going to go away. And we simply have a relationship now between velocities and altitudes. Another thing we can see is that velocity 1 is effectively 0. Well, actually, we're not. We could say that, but that's not where we're leading here. So let's go back. We have this relationship that says the 1/2 rho V squared plus rho GH sum at one point is the same as at the other point, since the pressures are the same. If we bring the kinetic energy terms, the 1/2 rho V squared terms, over onto one side, and the potential energy, rho GH terms, on the other, and these are kinetic and potential energy terms, so what we're seeing is an exact analogy to what we did in the preceding class, where we compared potential and kinetic energies. We see that the change in the 1/2 rho V squared is equal to the negative of the change in rho GH. You see we're subtracting state 2 from state 1 here and state 1 from state 2 here, hence the negative. And we also say that 1/2 rho V squared plus rho GH is constant. And this is going to be the case whenever pressure is constant. So whatever our change in 1/2 rho V squared, that's going to be the negative of our change in rho GH. Now what we've seen already is that when rho GH decreases, the 1/2 rho V squared increases. Or at least when the potential energy decreases, the kinetic increases. And that's exactly analogous to what we have here. This situation is simply a statement of energy conservation. It's just like saying 1/2 mv squared plus mgh is constant. Okay, if we multiply both sides by the volume, that's not velocity, that's volume, we in fact get rho times volume is going to give us mass. Here and here we have just 1/2 mv squared plus mgh equals constant. Now we can work through the details of Bernoulli's equation as we're doing here. If velocity 1 is 0, then we have a 0 here, and this side becomes 1/2 v2 squared. Up here, we've incidentally divided through by rho. It goes away. And we very quickly get velocity 2 equaling this square root, which is a square root of 2g times h1, which is square root of 2g times the h, which is exactly what we got in the preceding class.